Okay, so here we're looking at the dissolving process that happens whenever we make a solution. Um, it's not as easy as, oh, it's now a solution. It's a little bit more complex than that. So we're going to look at it at the molecular level. Okay, so first of all, when we're talking about molecules dissolving with other molecules, we have to go back to what we learned in the first unit about intermolecular forces. Okay, so in general, there is a rule that's called like dissolves like. So what that means is that substances that are polar will dissolve in solvents that are polar. So for example, water is an example of a polar solvent, right? So here's our water and we have a dipole there. So water is polar. So that means that other molecules that are also polar dissolve in water actually quite easily. Non-polar solutes dissolve in non-polar solvents. So for example, oil is a molecule that is non-polar. So that's actually why oil and water don't mix. It's because water is polar and oil is non-polar. So things that have opposite polarity will not dissolve very well with one another. Okay, so what is the reason for that? Basically, the solute particles have an attraction for each other, and the solvent particles have an attraction for each other. So in order for a proper mixture to happen in a solution, the solute and the solvent have to be able to interact with one another. So in order for something to dissolve in a solvent, it has to have interactions with the solute itself. So, for example, if these two did not want to attract each other, they would stay separated. There'd be no mixing whatsoever. But if you have similar properties, so if one is polar and the other is polar as well, you will have an interaction. So it really depends on the particles interacting with one another. There has to be a force of attraction, or else you're not going to have them come together. They're just going to stay separated. So water is known as, sometimes referred to as the universal solvent. So water is actually a great solvent, and it's used quite often. It's small particles, okay? They're very polar, and of course, we have easy access to it. So we can pretty much you can go to the grocery store and buy distilled water. Okay, it's very important though when we're talking about making solvents, like using water as a solvent, we're talking about just pure water. Okay, so tap water would not be a great solvent choice because tap water has a whole bunch of things already dissolved in it, right? So it has fluoride ions, it has chloride ions, a bunch of different things in it, because it helps to obviously disinfect the water so that it's safe to drink. So when we're making a solution with water, we want to make sure that it does not have anything else in it. So you would have to buy what's called distilled water. Actually, I think it's with an I. I'm horrible with that. But anyway, distilled water is just pure water particles. So, but you can actually purchase it anywhere. Actually, distilled water is a great, you can buy it in like big water coolers, or you can buy it in, big 2-liter jugs. They recommend using this type of water on different like coffee makers. So if your mom or dad have like a Keurig or a Tassimo or one of those ones that use the pods, they do say to use distilled water. That way it makes it as clean as possible in the machine. But anyways, the point is you can get it anywhere. You can go to Shoppers Drug Mart and pick up a thing of distilled water, okay? So because water is polar, it's able to dissolve a whole bunch of different polar substances. So, of course, The only thing water would not be able to dissolve is something that is nonpolar. So remember, the reason why it's polar is because it has a dipole. So the difference in electronegativity, right? So the difference in electronegativity between oxygen and hydrogen is a polar covalent bond, okay? And actually, this is a special type of dipole because it's between an oxygen and a hydrogen, which means it's an intermolecular force of hydrogen bonding. So if you forget what I'm talking about here, it's important you go back and review your notes on intermolecular forces. That's going to help you a lot when we're talking about solution interaction. Okay, so because water has such high intermolecular forces, it's able to attract the solute particles, which is why it's able to be such a great solvent. Okay, so some terms to know that we will be using in this unit is the term soluble or miscible or dissolved. These all mean exactly the same thing. So when we say that two things are soluble with one another, that basically means that the two things are able to dissolve. So for example, sugar and water. So we can say sugar is soluble in water. Or we can use the term miscible. Sugar is miscible in water, meaning sugar can dissolve in water. Okay? Then we have the opposite. Insoluble or immiscible means that its substance is not able to dissolve. So for example, oil in water. Oil is insoluble in water. Or we can say oil is immiscible in water. So the first two terms mean yes, the substance can dissolve. These terms mean no, the substance cannot dissolve. So if you're reading something or it's discussing solubility, right, the terms soluble and insoluble essentially mean dissolvable or not dissolvable. Okay, so polar molecular compounds. So polar compounds dissolve in polar solvents. We've already mentioned this. And actually, it's important to note that the closer related the particles are, the more easy, I should say, the easier it is for that substance to dissolve. So let's say you have a solvent that has hydrogen bonding. If you have a compound that has hydrogen bonding, it will dissolve even faster than it just being polar. If I have something that has dipole-dipole, it's still polar, but it might not dissolve as quickly as something that would have hydrogen bonding, let's say. So typically, the closer related the forces are of the solute and solvent, the easier that they will be able to dissolve with one another. So this is just showing you actually the interaction between a polar compound with water. So here are the water molecules. Okay, so here are my waters. And so the green circles are my waters. And you'll notice here there is another compound that is dissolved within it. So this picture here, so these would be my red particles, and my little waters are right here. So what this is showing you essentially is that if you notice, the red compounds also have hydrogen bonding. Notice how there's an OH group on it. So because this has an OH group on it and water has an OH group on it, those molecules are going to mix very easily, very quickly, because they're very similar. They all have LDF, dipole-dipole, and most importantly here, hydrogen bonding. And actually the same type of hydrogen bond, the OH bond. So remember, keep in mind that nonpolar compounds dissolve in nonpolar solvents. So an example of a nonpolar solvent could be gasoline or octane. Okay, so these are all hydrogens. So imagine that all these tick lines I'm going to draw are hydrogen atoms. Why, oh, why did I draw this big molecule? Okay, so this is octane. Octane is the main solvent for gasoline that we use for gasoline-powered cars, right? So octane is a liquid, and if you take a look at the structure, this is definitely non-polar. So that means that octane is actually a great non-polar solvent. So what that means is other things that are also non-polar will dissolve very easily in octane. But if you were to take water and try to dissolve it with octane, that would not mix very well, right? It would be insoluble because one is polar and the other one is non-polar. Okay, so give this a try. So I want you to draw the Lewis structure. So we haven't done this in a while, but I want you to draw the Lewis structure. And then after, you're going to tell me, is that substance soluble or insoluble in water? Okay, so hopefully you have the correct drawings. So here we have phosphorus, and we have our 3 chlorines, and you should have a lone pair. We'll come back and we'll talk about polarity. I just want to make sure we get the Lewis structure first. Carbon, we have our 3 hydrogens. Then there is an oxygen with a hydrogen. And carbon, we have fluorines all around. Okay, so remember that when you're looking at this for polarity, right, you want to look at the intermolecular, the electronegativity, and you want to make sure that you are looking at the symmetry of the molecule as well. So phosphorus has an electronegativity of 2.19 and chlorine is 3.16. So this is definitely a polar covalent bond. And because of the lone pair on the phosphorus, this will be polar. So you should have a dipole drawn pointing towards the chlorine between phosphorus and chlorine. So this is a polar molecule. Over here, you should have 2 dipoles, one drawn between the OH and one drawn between the CO. Again, this is a polar structure. And our CF4 is actually non-polar. Now, even though the bond here is polar, remember this is a symmetrical molecule because it's the same element. If you need to go back and rewatch the lesson on polar molecules, please make sure you go and do that. So, when we're saying if it's soluble or insoluble in water, if it's polar, it will be soluble, right? Because water is also polar. Polar and polar will mix, like dissolves like. So the first 2 are soluble and the last one will be insoluble.